Hello everybody and welcome to Electric Fields Lesson 5. Last lesson was more of a mathematical lesson. We looked at how to treat scalars and vectors differently mathematically. We're not really going to summarise that too much at the start of this lesson. We'll just move on to what we're going to do today. To start this lesson then, let's just have a quick reminder of what electric potential is and what it means. So the definition's there on the screen for you. The electric potential at a point in an electric field is the work done per unit charge in moving a small positive test charge from infinity to that point. Now from an equation point of view, we said that V is equal to Q over 4 pi epsilon naught R. And perhaps most importantly, we said that that was a scalar. Now let's take a charge. It doesn't matter which sign of charge it is. I'll just call it positive charge for now, just to make life easy for us. If I put a point here, just above the way that we've drawn it, the charge, using the equation, we can calculate what the potential at that point will be. We can take a second point correspondingly below the charge and we can calculate again what the potential will be at that point. Now, assuming that the distance from the charge to those points that I've drawn is exactly the same, the potential at those points will also be exactly the same. It doesn't matter the fact that one is one side of the charge and one point is the other side. Because we're dealing with a scalar here, the direction makes absolutely no difference and therefore the potential will be the same at those 2 points. We can keep on drawing in other points relative to the charge where the potential will be the same. And what we end up with, and you'll unfortunately have to excuse my drawing at the moment, I will show you a better diagram in just a few seconds time, we will end up with a map of points which is going to look like a circle. Now, again, I apologise that my circles on my writing pad aren't brilliant at the moment, but like I said, I'll show you a better diagram in a moment's time. So on that dotted line, any point on that dotted line will have exactly the same potential on it. We can draw a second one, and again you'll have to excuse my drawing, this is extremely difficult to do on the pad. We can draw a second line around which again will have exactly the same potential at all points. Now these lines are known as equipotentials. The clues in the title. Equi comes from the word equal, which we know just means the same, and obviously the rest of the word says potential. So it's just saying that these lines are lines of equal potential. Anywhere on that line, the potential will always be exactly the same value. So now I can show you a diagram that's nice and neat and doesn't rely on my ropey drawing skills using the writing pad. We can see then the field on the left hand side from previous lessons we know is a radial field. On the one on the right hand side is a uniform electric field. On the diagram we can see two different things happening. The blue lines on both of them are the field lines, the lines of electric field. Remember, lines of electric field are lines of action of force acting on a small positive test charge. We also have the dotted lines which represent our equipotentials. For a radial field we can see that the equipotentials form concentric circles around the charge. In a uniform field, they form straight lines which are parallel to the plates themselves. What we can notice straight away, if we think about the radial field first, the field lines follow radii of a circle. That's where we get the word radial from. And the equipotentials themselves form concentric circles. In the uniform field, the field lines are moving perpendicular to the plate, right to left, from positive to negative, whereas the equipotentials are parallel to the plates. In both cases and in both diagrams, we can see that the equipotentials and the field lines are perpendicular to each other. And that's a general rule, that equipotentials will always be perpendicular to electric field lines. And in fact, that rule will hold true no matter how complicated our diagram might be. Now, at the bottom of the screen there, you can see two examples of where two electric fields are interacting. On the left-hand diagram, we have two positive charges, and on the right-hand diagram, we have a positive and a negative charge. Now, on the right-hand diagram, the field lines are now starting to look very similar to how you would have studied field lines when you were looking at magnets and magnetic fields back at GCSE. What we can notice though is that in both of them, still that rule holds true, where at any point the equipotentials are at right angles, they are perpendicular to the field lines. Now, the way that I was always taught to look at equipotentials and to view equipotentials is very similar to how contours on a map will work. If we think about the map first, hopefully one of the things we know is that in areas where the contours are close together, that represents very steep ground. So if we have a look in this top right hand area of our map, we can see that the contours are close together, and that represents what should be quite a steep incline. If we have a look nearer the middle of the map in this area here, the contour lines are very far apart, so if I was walking in that area, I would expect that ground to be a lot flatter than the area obviously in the top right hand corner. Coming back to our equipotentials then, what it means for the electric field is that in areas where the equipotentials are close together, that represents a strong electric field. The electric field strength will be quite high. Looking at the diagram, that's in the area close to the charge. If we remind ourselves of the radial field electric field equation, Q over 4 pi epsilon naught r squared, because we're close in to the charge itself, R will be small, and because R is on the bottom of the equation, E will therefore end up large relatively. If we go further out into this region here, the equipotentials have moved further apart. Larger distance will mean a smaller electric field. Going back to the equation, R has increased, and because it's on the bottom of the equation, E will therefore have decreased, and we know that from our knowledge of inverse square laws. What that then leads us on to is the idea of a potential gradient. We had the idea of a gradient from contour lines on a map, and we can now have a look at the gradient, in a way, of the electric field when we're dealing with equipotentials. Now, just to make life nice and easy, on the screen I've shown you a uniform electric field, and what I'll do is I'll just start throwing some numbers on. We will give the plate over here a potential of 0 volts, and we will give the plate over here a potential of 70 volts. Our dotted lines in between are equipotentials, and because this is a uniform electric field, each equipotential represents a decrease of 10 volts as we go through. So 30, 20 and 10 down to 0. What we can see here then is that our equipotentials are equally spaced apart. Each of the distances between these dotted lines is the same. What that would represent from a gradient point of view is a constant gradient, and the gradient therefore shows us what the field strength is doing. It's a constant field strength in between. Now that hopefully should be expected. Because we're dealing with parallel plates here, we are expecting to see a constant electric field in between the two parallel plates. We know, of course, that the electric field strength in between parallel plates is given by the equation E is equal to V over D, where V is the potential difference and D is the distance between the two plates. If we want to make this equation more generalised and take this idea of potential gradient into account, we're going to rewrite it as E is equal to negative, I'll explain the negative sign in a moment, delta V by delta R. From a dimensional point of view, we're still dealing with exactly the same units. V and delta V have the same units, D and delta R are both distances and they have the same units as well. Now the reason why we have a negative sign, if we think about the electric field in this diagram, the electric field is in that direction. It goes from positive to negative. However, if we have a look at the numbers from the potentials and the numbers on the equipotentials, they are increasing in that direction. Therefore, we have to put the negative sign in to compensate for these two opposite directions in electric field and potential gradient. This delta V by delta R then represents our potential gradient. And if we just think about what we said earlier about delta R, that as delta R increases, in other words, we move our equipotentials further apart, what that will mean is that our electric field strength will decrease. The same will go the other way around. As delta R decreases, E will therefore increase. And that makes perfect sense. Hopefully, going back to that diagram and the explanation that we used with the contours. We can also see that as delta V increases, our electric field strength will increase as well. On our diagram at the moment, we have a difference between two equipotentials of 10 volts. If we were to keep the diagram exactly the same, but increase that delta V to 20 volts every time, then the numbers would very soon become 20, 40, 60, 80, 100, 120, 140. We've doubled the potential difference between the two plates, and therefore we must have doubled the electric field strength between the plates as well. One of the advantages of using equipotentials is to be able to calculate the work done in moving a charge. If we were to start a charge, a small positive test charge, on this equipotential here, and we were to move it to a different equipotential, we will have moved it a distance delta R. By moving it, we have also had to do work in order to bring it closer to the charge in the centre, and we know that because we're dealing with two positive charges, work has to be done to bring it closer. From that, we can calculate the change in potential, the potential difference between our 2 points, V1 and V2. And we know that change in potential is always V2 minus V1. From a couple of lessons ago, the equation delta W is equal to Q delta V applies, and we can therefore calculate what the work done in moving that small positive test charge from point 1 to point 2 will be. Now, interestingly, if we take 2 points, I'll take this point here, V1, and I will take a point here, V2. And we're going to imagine moving a charge, a small positive test charge, from point 1 to point 2. What will be the work done in moving a small positive test charge from that point labelled V1 to that point V2? Well, firstly, we have to think about what the potential difference is. Well, in this case, because V1 and V2 are both on the same equipotential, V1 and V2 must therefore have the same potential, the same value for potential. As we said earlier, the fact that they are located in different positions on that equipotential makes absolutely no difference. Because we're dealing with a scalar, direction doesn't come into play, and therefore the values are exactly the same. Delta V, or the potential difference in that case, will therefore be 0, because V2 minus V1, as they are the same values, you subtract the same thing from itself and you end up with 0. The work done in moving it from that point to the other point is therefore 0. In other words, any object that moves along an equipotential, and we can quite easily see that this would apply to something in orbit, and this is where we can now start to link our electric fields topic to our circular motion topic, that any object that is moving along an equipotential, no work is being done in keeping that object orbiting. In this case, a charge. We can see how that can therefore relate to an electron orbiting in a hydrogen atom, and it will also apply to any other circular motion example that you can think of. On then to an example. This is again an AQA past paper question from 2002, so from a long time ago, but as I always say, we know full well the physics stays exactly the same. So the question says, the diagram shows how the electric potential varies along a line XX primed in an electric field. What will be the electric field strength at point P on XX prime, which is midway between R and S? And it gives you the multiple choice selection there. As usual, pause the video, have a think about it, and come back when you've got an answer. Now, what we notice straight away is that all of these vertical lines are all equipotentials. At any point on those lines, we will have no change in potential whatsoever. So they are equipotentials. We also notice that they are all equally spaced apart. The distance between the 50 volt line and the 40 volt line is half a metre, as is the distance between the 20 volt line and the 10 volt line. What we can see straight away then is that we have a uniform electric field. That then means that a lot of this question is completely and utterly irrelevant. All it's asking us is, what's the electric field strength? Because the electric field strength at any point in between there and there, because it's a uniform electric field, will be exactly the same. If we have a look in the region that we're talking about though, we can see that the change in potential, delta V, between our 2 points is 10 volts. Our change in distance, our delta R, is 0.5 metres. And therefore, using the equation, E is equal to negative delta V by delta R, we can take 10 and we can divide it by 0.5, and that will give us an answer of 20 volts per metre. Yes, I am aware that I've dropped the negative sign at that point, but it's distance or direction in this question is completely irrelevant, and therefore we can ignore it. And there we have the answer. The answer is C, 20 volts per metre. So to summarise then, today we've looked at two key ideas. We've looked at equipotentials, and equipotentials are lines of equal potential. Secondly, we looked at potential gradients and we had the equation E is equal to negative delta V over delta R, where delta V divided by delta R is the potential gradient. So that's the end of this video, and in fact that's the end of the topic as well. So with obviously the topic as a whole in mind, I hope you've enjoyed that. I hope you've got something useful out of it, and it's useful to you, whether it be in sort of just general learning or revision or anything like that. Don't forget to check out the other topics that are either on already or will be coming very soon.